purpose of the simulation was to generate power, to power the AI and the robots from human brain. So Landauer in 1960s, he recognized that computational processes should be treated through the prism of laws of physics and thermodynamics, just like any other processes. And we had in 1905 special relativity, and we understood that the dynamics of things moving at relativistic speeds is very different to the Newtonian dynamics. So it's called relativistic mechanics, okay, not classical mechanics. This is what time does around black holes. The black hole horizon, it stops completely. There is no time flowing.
Scientist becomes an apostate. For
Yes,
want of another religious expression.
And it does bring about the necessity of a creator, of a simulator, if you want, of some kind of entity that does this, to bring some contradiction in terms of evolutionary theory. My work points to the fact that genetic mutations appear to be driven by a hidden entropic force, this second law of information dynamics. So they are not random.
Professor Melvin Vopson, thank you so much for joining me. I'm really excited and looking forward to this conversation. Thank you.
Thank you, Conor, for having me. Good morning.
Good morning. So can you tell me, give us a quick synopsis of your background, where you're from, and your journey into information physics?
So I did a PhD in condensed matter magnetism at the University of Central Lancashire, graduation in 2002, essentially. So, and prior to this postgraduate scholarship, I was at the University of Bucharest, Romania, where I did my first BSc in physics, and that was followed by a master's degree in physics at the same university. So yeah, I was born in Romania, and I spent my past 24 years in the UK. Joining here initially for a PhD program, and I was offered a postdoctoral research role at the University of York in 2002. And it was only 1 year, but it was a really interesting project, In fact, I had a 10-year offer at a research institute in Dresden at the same time, and I had 1-year job offer at the University of York. And I chose 1 year at York instead of 10 years in Dresden because the project was really interesting. So and from there, it kind of cascaded through another postdoctoral role at York for another 4 years on a different project. I ended up making UK my second home, I suppose. Since 2012, I'm a permanent academic at the University of Portsmouth. But prior to that, I spent many years at the National Institute of Physics. It's called National Physical Laboratory. Is the equivalent of Max Planck in Germany or NIST in the United States.
And tell me, did you have a kind of a Newtonian apple moment where you thought, okay, physics, this is the path for me? Or was it kind of a gradual process? Were you particularly good at math as a young man? Or?
Actually, as a young man, my first love in life was tennis. So I'm coming from a tennis background. I'm an ex-junior pro, and in fact, I'm coaching my young boys, my 2 sons. They're at the top of their game in the UK, national pathway and county champions, and it's all my entire work. Actually, I'm coaching them every day. Yes, I was very good at maths and physics and analytical thinking, and I was quite capable, relative to my peers, and it was visible from a young age. Most striking was finishing math tests. in a fraction of the time of the other colleagues basically would do it.
Mm.
But tennis was my target, and it ended with an accident. So I had to withdraw from performance tennis and make a choice, choose an academic career. And yeah, physics came naturally because it combines mathematics and the natural world, you know, and to some degree chemistry. So I thought it captures everything and is really fascinating. Mathematics can be quite boring at some times because it's too detached from reality, it's too abstract. But physics gives some essence to equations, some meaning, and is more pleasant to actually do research in physics. Yeah.
You've written a book called Reality Reloaded. So let's start at the beginning. What is the simulated universe hypothesis?
Well, frankly, Conor, this is at the basis of everything. This is a philosophical theory. So my hope is that the work I've been doing and the work others are doing as well will bring this philosophical idea into the mainstream science. And there are some things that we uncovered, and we can't any longer ignore some of the evidence that we have that this could be a real possibility. Okay, that the whole universe is a digital construct. The simulation theory it goes as far back as Plato. Frankly, it was the idealist thinkers that assume that the real world is not what it seems. It's just a projection of our own minds. Actually, that was the thinking back then, and the only thing real is our consciousness and our minds, and everything around us is our own construct, the world around us. And it takes you back to the allegorical cave, Plato's cave, and you know, the projections on the wall of shadows. And so very interesting ideas going very long time ago. But the simulation hypothesis has morphed into something different. The modern iteration of this philosophy is idealism, is that it assumes that ourselves and our minds are actually part of the simulation as well. So unlike the idealist thinkers that they positioned our consciousness at the core of everything, and the world being a construct of our own minds, the simulation hypothesis, the modern iteration of this philosophical idea, is that everything is actually a construct, including ourselves and our consciousness and our minds. And this has entered the popular culture through movies and science fiction books and all sorts of things. Everybody is familiar with the Matrix movie, and exactly. There is increasing evidence and signatures of this being a real possibility. Okay, and it can no longer be ignored, because for the simple reason that we have too many unanswered questions in physics and about the universe and the world. And as long as we are unable to address these questions, and I'm talking about the big things like the Big Bang and the beginning of everything and the nature of the universe, and the missing 95% of the universe, what is all that stuff, the dark matter, dark energy, all these things, as long as we don't have viable explanations yet, this simulation hypothesis becomes a feasible avenue for research. And it does appear as sweeping under the carpet the big questions and the heavy stuff, and a bit of cheating, saying a bit like the religious people would do in the past, that there was an unexplained phenomenon, and they would say it's God's will, or it's God's anger, or it's God's, this. We came a long way, and we explained most of these things, and we understand. I'm not denying religion. I'm just saying we used to take the short the shortest pathway and the simplest explanation and blame something on divine or and there's a danger that this could be seen as a similar thing in science, claiming that we are in a simulation and things we can't explain are because of that, and yeah. But in reality, this raises more questions than answers. So it doesn't stop the science, or it doesn't suppress the science. In fact, it stimulates the scientific process even more to actually explore everything we know almost from this new angle and try to understand the things that we couldn't understand before. So it's not a cheap way of brushing under the carpet complex scientific questions. No, it's actually complicating even more our scientific process. It's not an easy way out.
So at the core of the book, in some ways you're refuting the second law of thermodynamics, right? The law of entropy.
No, I'm not at all. So all my work is the beauty of all my work is that it doesn't contradict anything in physics. Okay, it does.
Okay.
When you go against Boltzmann or Einstein or Maxwell or Newton or something like that, then it's hard to go to bed at night and sleep tight. I'm telling you, it's not a very brave thing to do. Okay, in science, I'm not doing any of that.
Yeah.
But I do contradict something, actually. I do bring some contradiction in terms of evolutionary theory. My work points to the fact that genetic mutations appear to be driven by a hidden entropic force, this second law of information dynamics. So they are not random. They are not random. And Darwin's evolution theory states that genetic mutations are complete random processes. There's nothing governing these mutations. The only thing that governs evolution is the natural selection. So if a mutation is beneficial to some organism, it will be kept and passed on to the next generation. If it's detrimental, it will be erased through the natural selection process. But the mutations themselves are just random. So my research kind of contradicts this, and there is some solid evidence actually for this. But in terms of physics and fundamental laws, I'm not going against anyone, and I'm not contradicting second law of thermodynamics or Boltzmann. All I'm saying is that there is another second law, second law of information dynamics. So this one, we need to make a clear distinction here. The second law of information dynamics is applicable to information, to systems that can store information. Okay, so the information storage systems, if you want. But it does appear that anything can be actually defined as an information storage system, or anything where you have a probabilistic nature of events and processes, then information kicks in. So it could be, but it's not against the second law of thermodynamics. It's complementary, if you want. It works. They work together.
Yeah. Okay, so a simulated universe would indicate that there is code underpinning the universe and wired into the simulation. How would you find, locate, identify that code? Is that the next frontier?
So you actually, the way you formulate your question is actually very constructive, and this is the way I explain the existing work and the future work, because what you just said is very, very fundamental. Okay, so very frequently in scientific process, to solve a problem, whether it's mathematics or physics, we have a formalism where you make an assumption, okay, and then based on that assumption, we construct a whole formalism. It could be experimental protocols or theoretical arguments. And at some point, starting from that assumption, you reach some kind of conclusion, okay? And if that conclusion contradicts what we know already that is true, it means the assumption most likely was wrong, because it led you to a contradiction. Or if the assumption was correct, it should take you to some kind of truth, some kind of fact that is already proven and known. So on the same basis, coming back to your question, let's assume that we live in a simulation. Okay, let's make this assumption. So working on this assumption, you will start finding from inside the simulation some kind of evidence that this is true, okay, or some kind of scientific proof. And at some point, we either find a contradiction that it's illogical, it violates everything we know, and it will invalidate the original assumption. So it means we are not in a simulation. Or at some point, we reach some valid conclusions, some truth, and it means that this assumption is supported by evidence. Okay, so it probably is true. So let's assume that we live in a simulation. Then what tools do we have? What kind of in our scientific toolbox, what kind of tools we can deploy to prove this, from inside? It's a very serious scientific challenge. It's not an easy thing, okay? And there are three, I can't think of, I wish I could, but there are three different directions you can identify. Two which are revolving around my own research, and one which is not part of my approach, and I kind of disagree with that. And I'm going to start with that one first. The first is having the way you formulate your question, the existence of a code running the simulation. So that's very, very powerful. So if we assume that we are in a simulation, then that means the first logical transition from that assumption is that there is a code, some kind of code. We don't know the nature of the code. Is this digital? Is it quantum computation? We don't know what is the computational process, but there will be some kind of code running this. So you need to find evidence of the code from inside the code and evidence of the data, huge amounts of data that would propagate the code and make this code function. And when I say data, I really refer to information, digital data, or some kind of information that has to be there, okay, which is the code itself, all the variables and all the information storage and all the data stored as part of the running the simulation. So then I said there are three approaches. The first one is being suggested by other scientists to look for glitches in the simulation. Okay, so like any program, I had my computer last night crashing very bizarrely. You just had a crash now of your Zoom application. So occasionally you have some glitches in the program, and the idea is that if you can find some glitches in our universe, okay, it might be an indication of the glitch in the code. And when I say glitches, I'm not talking about UFOs or ghost apparitions or this kind of stuff, paranormal things. I'm talking about violations of the laws of physics in a short time segment, in a little localized space-time region, things that don't make sense and they contradict everything we know. So that would be some kind of indication of the glitch in the simulation. The problem I have with this approach is that the laws of physics are continuously evolving. We are developing our understanding of the universe on a continuous basis, and you can just look at the classical mechanics if you want, the Newtonian dynamics. We not long ago we thought is all there is. It explains everything. Is the dynamics of large objects, small objects, whatever. It's a beautiful theory. But then we had in 1905 special relativity, and we understood that the dynamics of things moving at relativistic speeds is very different to the Newtonian dynamics. So it's called relativistic mechanics, okay, not classical mechanics. And then not long after that, we developed an extension of this called quantum mechanics to explain the dynamics of things at quantum level, like atomistic level and subatomistic level. So in other words, if you would observe, before we develop these new theories, if you would observe something that appeared to be a glitch in the simulation, it was just our lack of understanding or our, very immature, if you want, understanding of the laws of physics, which are continuously evolving. So this approach is maybe not the best, the scientific approach, because
The glitch
we
may
don't.
not, in fact, be a glitch. It may be
It might be
lack
something
of
that we don't
understanding on our side.
exactly. That's exactly how to put it. And besides, we don't have a reference frame to distinguish what is real and what is not real. So it's not a good approach. But the other two, looking for what you just said in your question, looking for the code or looking for the data of the code. Okay, these are very viable propositions, and I've seen some interesting ideas. For example, looking for the code is maybe if you overload the computational power of the universe in a local space-time volume, you give it's almost like a DDoS attack on the universe itself. The idea is that if you can engineer something like this, the time will slow down, just like in the relativistic mechanics. It will slow down in that region of space-time, because this is exactly what a computer does if you overload your computer with too many applications being open at the same time, and the processor and the memory is being overloaded and is not capable of handling all the applications and the computational processes. What it does is slows down. Everything starts moving slowly, and the computation is being delayed, and so that would be the equivalent of a DDoS attack on the universe. You should see some kind of time slowing down, or some kind of gravitational anomalies in that region. And this is what time does around black holes. The black hole horizon, it stops completely. There is no time flowing. And at relativistic speeds, it is exactly what it does. The time flows slower for objects moving at relativistic speeds and stops completely at the speed of light. And that is these are little hints that we have in science, that just like a computer and like a computational process that has a limited processing power, a processor running at, I don't know, 5 gigahertz or whatever, that's the processing speed of the processor. You cannot overcome that. We also have a limited processing speed, is the speed of light.
How would you test that? How would you run the experiment?
That's the $1 million question, and the Nobel Prize winning research. I mean, if I knew how to do that, I would do it tomorrow, but I don't have a clue. And I've been exchanging emails with some very smart guys, and there are suggestions, there are hints of how one might go about this, but it's totally unachievable as far as I know. We don't have a protocol yet. So that is an approach, okay. But another approach is to actually look for some signatures of the code in the universe, okay. And I think this is what I found with the second law of thermodynamics, second law of information dynamics. Yeah, I think this is it's not the evidence. I can't. Everybody gets excited about this aspect of we live in a simulation and all that, but actually, this is just a conclusion, a tiny conclusion, a possible conclusion. It's not even. I'm not claiming I found the total proof. All I'm saying is some kind of supporting evidence to this, and it needs obviously more research. But I am excited about the second law of information dynamics itself, because we have an additional tool now in physics to look at a variety of phenomena, including biological systems and DNA, RNA, other things. But this appears to give some support to this idea, some kind of, it's like a fingerprint, if you want, like some kind of supporting evidence of a signature of this code, because it appears to permeate everything. It's quite universal, and it's really applicable even to mathematical entities like geometric shapes and symmetries and this kind of stuff. Very abstract things. They are not physical. They are not material things. So yeah, it's quite powerful. Yeah. So that is one way of building up a case around this idea, a scientific case, I should say.
Quick, brief interruption. If you've ever watched one of the videos, if you're watching this one now and you're enjoying it and you find it interesting, could you please hit the subscribe button? You've no idea the difference it makes to a channel and to a video and how it's proliferated across YouTube. It really does matter. If you could do that, I would really, really appreciate it. And to all those that have done it already, thank you so much. I really appreciate each and every one of you. Thank you. Well, what can you tell us about the math that you're using to do?
So the beauty about this is that the mathematics behind this is highly accessible. It's not it's actually, first of all, it's classical. Everything is classical, so it's nothing quantum formalism in anything I've done. It's nothing relativistic either. Okay, so we are not looking at tensor calculations and you know, quantum field theory or anything like that. It's actually very accessible mathematics, very easy to understand, and perhaps this is why the uptake is so good actually, because it's highly accessible to a very wide range of scientists and public. So what is the mathematics? Essentially, the first, it's a bit of physics. So the idea that I don't know where to begin, because there are two things here. There is I explained there are three possible signatures: the glitches, the code, and then the information. And I said nothing about the information itself. Okay, so finding the information. So this is another piece of work I've done in 2019 called mass energy information equivalence principle. So perhaps I'll get back to that in a few seconds. But essentially, the idea is that when you have information created into a physical system, the intuition tells us that you actually order that system, and you create order in the system, and you lower the entropy. It's actually the opposite. You you actually increase the entropy of the system by creating additional information microstates. So the system had an entropy, a measure of disorder, or the microstates that are compatible with the macrostate of the system at the time zero, and then you put information on that. The entropy increases because you add information states. So this is, it's hard to picture this, but actually this is what is happening. Okay, so if you create n bits of information, you will have 2 to the power n microstates added to the system. So it increases very rapidly. And if you decide to delete now some of that information, okay, what you essentially do, you reduce the entropy. Okay, so you go against the second law of thermodynamics by reducing the entropy. So that cannot happen. Okay, so and there are two things here in this process. First, once you delete the information, this is an irreversible process. So in other words, once you delete a file from your computer, it will not spontaneously appear by itself again. You need to add energy and rewrite it and you know, reconstruct that file. But by itself, it will not reconstruct itself. So it's irreversible process. And we know from thermodynamics, irreversible processes are dissipative. So they have to dissipate some energy. So for example, I give you this coffee example. It was very hot at the very beginning when I joined this Zoom interview. And it goes through an irreversible process by dissipating energy to the room and to the coffee mug. At some point, you will reach room temperature. And this is irreversible. It will not spontaneously heat itself again. It will stay like that, okay? So Landauer in 1960s, he recognized that computational processes should be treated through the prism of laws of physics and thermodynamics, just like any other processes. In other words, if you have a logic computational process that is irreversible, that should be dissipative, just like this coffee or like any other physical system. And he concluded that information, when you erase it, should dissipate some energy. Okay, and that energy comes from the information itself. It's nothing to do with the physical support, where the information, the physical states where the information is stored. This information, this abstract mathematical construct itself that gives us the extra entropy states, the information, the energy dissipation comes from the information. So he said information is physical.
It has mass.
Well, no, I said that. Landauer said it's physical. Okay, information is, it has energy. So all I did in the 2019 article was to connect the dots. I said if information is equivalent to energy, and if energy is equivalent to mass, which is, we know this from Einstein, then energy, mass, and information are all the same entity, a triad of the same entity. So what is, you are asking about the mathematics of this. So first of all, it's the Shannon information theory that is fundamental to this. In 1940s, Claude Shannon, so this is a American mathematician. In 1940s, he formulated what we call the information theory, and I believe his job was to find the most optimal way of transferring data or a message, he calls it a message, from point A to point B, using the most optimal amount of information to make the message decodable at the other end. So maybe if I say Conor, okay, and if I take a letter out of your name, okay, and send this message to somebody, and that somebody knows is a name, you will go through all the permutations and all the possibilities of combining letters to form a name with the remaining letters and few of them missing. And they will, the question is, what is the minimum amount of letters in that name that you need to send to make it decodable, so somebody can figure out this is a Conor. It's not, there is no other possibility to form a real name from these letters unless it's a Conor, okay? So, and he gave a formula for this. It's called the information entropy. So essentially, he gives the best data compression, but the beauty of his theory is that he called these letters or messages, but he calls them events, and he allocates probabilities to them. And then you can take that theory and apply it to anything that can have a probability, can be called an event. So digital data would be a message of zeros and ones. Genetic data will be a message of 4 letters, A, C, T, G. Okay, so the nucleotides are encoded in 4 letters. So Shannon's theory has found applicability in linguistics, in mathematics, in physics, in biology, in genetics. It's incredible. Okay, digital technologies, and he gave us the unit of bit, a bit of information. The 1 bit, we measure digital data and the size of digital files and the size of digital data in units of bits. He gave us this unit, okay? It comes from the Shannon's information entropy. So that comes back to this mathematical aspect. So what is information? So when you say information, it means different things to different people. It's a context-dependent, concept. But when I talk about information, I really mean a mathematical function, this Shannon information function, which is a logarithmic function of a probability of an event to occur or not, okay? This is in a nutshell, this is how you define the information. And
Melvin, information has to be communicable, right? So it has to have a language.
Yes and no. It's a good point, but this, you see, in this formalism, the information is defined only like this, and there is no measure of the quality of the information or other features of the information. So in this respect, if you take a string of zeros and ones and you put them on a data storage, and they are completely randomized and they mean nothing, from the information theory angle, those bits represent information. You can allocate a bit measure to them, and you can calculate an information entropy. But if you actually retrieve the message that those bits will form, there is gibberish stuff, is nothing there. If you take the same amount of bits now, and maybe you write a message that contains, I don't know, the mystery who killed Kennedy, or some kind of great information, okay, that is encoded in those bits. Shannon information theory does not make any distinction between completely random, non-message, if you want, information that is encoded in those zeros and ones, and something that is hugely valuable. So it doesn't give you a value of information, of quality of information. And I think this is a bit of a gap in the theory. It just treats information as probabilistic events. So it looks at the probabilities of these zeros and ones to occur, and it draws a value of yeah. So yeah, it's not. It doesn't give you a color of of something or features, other features. Only a simple value in bits. Yeah.
So so you've described the math there, right? Have you? Can I ask you about AI and what impact AI, the human development of AI, could have on the simulation? Is that a question that has occurred to you?
It's not only a question that occurred to me, but the only reason we are talking about this, and the only reason Landauer in 1960s started to examine computational processes from the angle of the laws of physics, applying the laws of physics to computational processes, and formulated his Landauer principle, is amazing stuff. The only reason we've been doing this is because we developed quite recently digital technologies. Okay, so the first transistor and semiconductor devices, they were invented in 1940s. There was a Nobel Prize for that. In 1952, we had the invention of the microchip and the integrated circuits. So this lithography process and vertical integration at nano level, layer by layer, and these insane processes that we do to fabricate the high-tech gadgets of today. And you can look back, and this is a very recent history. I mean, we are looking from computational things. Started IBM in 1956, developed the first hard disk drive. So the very first computers around there, okay, around 1950s, 1960s. But this is what triggered this new, if you want, angle of looking at physics and the world from computational processes angle, and from the rules of computation, if you want, and start looking at similarities between the way the universe behaves and how a computer behaves, even however basic. Okay. We came a long way. I mean, if you take the Apollo mission, the whole NASA station that was deployed for the Apollo mission, in your pocket now, your mobile phone has more computational power than the entire Apollo mission computer. Okay, so it's incredible the rate of development that we are experiencing now, and how fast we move into these computational technologies. I mean, for God's sake, we have immersive virtual realities now. I even I have home a PlayStation system that has a VR add-on to it, the PS4 and above. They come with a VR component, so you can do VR games and immersive VR applications. Is quite remarkable, and this is in a tiny short space of time. And then in the last year or so, we had the emergence of something else, which has been theorized and speculated for a long time, the artificial intelligence. But this is no longer science fiction. This is now happening, and it's happening very fast, so fast that the British government had a recent global summit on AI, looking at safety nets around this, looking at possible regulations, because left unchecked, this has the potential to be very it has the potential to be very helpful to mankind and to our progress, but also very destructive. It's a bit like atomic bomb. Okay, so when we discovered how to split the atom and how to make extract atomic energy, you had the two sides of it, the good and the bad. The good was the generation of power using the atomic power plants, and the bad is the defense component and the weapon systems that have been developed on this. Well, I see the AI in the same way. I see the AI artificial intelligence as a very good force for good, a very powerful force for good, but also a very dangerous.
What I'm wondering, Melvin, is with the accelerated advance of AI, right? I mean, it's anticipated in the next few years that we're going to have large language models and AI that will pass out
Overcome human brain,
intelligence,
and yeah.
right?
I think it's already happening. I think it's not in the future. I think this is already happening. It
So
has
you would,
happened.
yeah. So you would have to wonder, with the emergence of AI technology and the possibility of a simulated, how does the AI technology sit within that framework, that simulated units, and what can we learn potentially?
Okay, so if you actually go back to the original Matrix movie, okay, and I'm sure many of your listeners are familiar with this movie, the simulation was actually run by a kind of AI, okay, and the purpose of the simulation was to generate power, to power the AI and the robots from human brain. So it kind of geniusly, you know, when they wrote the script and all that, I mean, to come up with this back then, it was amazing. Now you mentioned my book, okay, very kindly at the beginning. So in my book, I discuss this scientific case for a simulated universe. Okay, it has an academic component there. There are some equations and all that, but there is a lot of philosophical discussion. And at some point, I realized that talking about universe and the world being a simulation, it can be quite threatening and quite, you know, unwelcomed by a very large group of deeply religious people. Okay, so you have different denominations, different religions on the planet. Billions of people are worshipping some kind of divine. And when you come up and say this, it could be seen as blasphemic, you know, like, you know, this is an assault to our beliefs or our religion, you know,
But I thought it would be
foundations.
it
And
infers evidence of intelligent design, though.
that's exactly so. I'm getting there. Exactly, this is what I'm doing. So what I write in the book, I said, okay, I made myself a bit of a target to these people, and I better address their concerns and have a little chapter about this in the book. It's called The Religious Perspective to the Simulated Universe Theory. How religion and this idea, what are the synergies and how they complement each other, and do they contradict each other? And actually, I make a strong case that the simulated universe is not denying a religious divine, is actually saying almost the same thing. It does bring about this intelligent design. It does bring about the necessity of a creator, of a simulator, if you want, of some kind of entity that does this. And so I think I did quite elegantly write. It's a short chapter. It's not very large, okay, but I think I managed to calm down a lot of these people that would be probably angered or threatened or anything. However, in the process of doing this, I had to get a little bit deep into the some of the biblical things, you know, some just essentially look at the Bible really, and you would not believe what I found. You would just not believe what I found. I found a paragraph in the Bible, is Gospel of John, okay, and I might not say it word for word exactly how it is, but it is like this. At the beginning, and it talks about the Genesis and how the world started. Okay, at the beginning there was the Word. Okay, Word, and the Word was with God, and God was the Word. I don't know about you, but it gives me goosebumps. This paragraph, because you just take this word and replace it with the code. And read again the paragraph, okay, from the Bible. And the Bible says, at the beginning, there was the code. The code was with God. So it tells us there is a creator, there is an intelligent design that wrote the program. And then it tells us who the God is. It says, and God was the code. In other words, God is an AI. And this is in the Bible. how insane is this? Okay, because you just brought about this AI thing, and it coincidentally, I mean, I have this in the book actually discussed in a few other paragraphs. I know it sounds like cherry picking. You go and pick up things and start making things out of, giving them your own interpretation. And of course, if you have a hammer, everything looks like a nail. You know how they say, yeah. So I know it sounds like this, but you can't deny the powerful, similarity between. I mean, we just had AI emerging in the last couple of years, and to have the Bible telling us that at the beginning there was nothing, just the code, and the code was with the Creator, and the Creator was the code. In
What
other
can
words,
you remember the passage from the Bible, or where can people locate that?
Gospel of John 1:1. So first paragraph, 1:1, and it's in the book actually, the whole code and a few other codes. So I thought that was quite powerful. So what started as a almost apologetic little chapter to religious people and everything, I ended up actually endorsing the whole bloody thing, and like saying, wait a second, even the Bible tells us that we might be living in a simulation. So how crazy is that?
Are there many physicists that share your perspective, or your, like, well, what is the reaction from your community, being the scientific community, to the book?
So all the time when some new idea or some new paradigm emerged in science or physics, the first reaction was to some kind of reluctance, some kind of push, some kind of reluctance at accepting it. I mean, when Planck came up with the idea that the energy is quantized and we have quanta of energies, and we had all these people doing calculus and differential equations and continuous functions and mathematics, and you say, wait, everything is discontinued, everything is discrete, and the world, it doesn't function the way we thought it does. And I mean, he was so scared of his own statement. If I remember correctly, for about 2 years he did not go to any conference, he didn't make any public statements. He just took a step back and said, gosh, I'm just gonna wait and see what happens. So quantum mechanics told us weird things, the non-locality, the quantum entanglement, the duality of wave particle, the double slit experiment, which depends on the observation. So if you look or if you observe the experiment, it behaves in one way. If you don't, it behaves as a wave, so it doesn't collapse the wave. I mean, these are really weird things that the science threw at us, and we learn how to accept them. But
in many ways, the scientist becomes an apostate, for want of another religious expression.
Well, sort of, yes. And the initial reaction is to reject everything, but then we have the scientific process, and this involves empirical evidence. It involves further
testing,
development, further development of the theories. Looking at that method, which you start with a conjecture or some kind of assumption, and you build your work from that. You reach a valid conclusion, then maybe the assumption was correct. So these kind of tests that we have. So the way I see it is, the duty of a scientist is to actually share the science and publish any ideas and any new science and everything. Because if we don't, it's actually very detrimental to the scientific community, and we stop the progress if we don't share the scientific findings or ideas. Sometimes these will be disproved, other times they will be proven correct, okay? But if you don't put them in the public domain and put them up for debate and scientific scrutiny, if you want, yes, then you never know. So just imagine if Newton wouldn't publish his work, or Einstein, or we would be set back hundreds of years in terms of development.
So it takes a certain amount of courage.
It's not courage, it's a public duty. It's a public duty. If you do science, most of us are funded by taxpayers through the university funding systems and research grants and things like that, okay? Research institutes. Most of us are in public duty service jobs, as I see it. And it's a public duty. It's your duty to share your science. And yes, absolutely fine. Sometimes people do mistakes, and or something is wrong, but if you don't share it, we will never know, do we? So no, it's a public duty. It's not. I don't see it as courage or anything. I'm not doing anything wrong. I'm just, this is the science. This is where my conclusions took me. I might be correct, I might be wrong, but I can't solve this on my own. There are thousands of other people out there that they deserve to read about this, and maybe they will come back and disprove it, or maybe they will come back and say, hey, this is really helpful because the second law of information dynamics, it helps us to explain things that we couldn't before, or things like that. Okay. So that's how I see it. It's not, I just hope the uptake is positive and is fine. But always there will be some push, like you said. And I'm happy with that. I accept it and I welcome it. In fact, I welcome debate, welcome criticism. There is no reason why you wouldn't. The scientific debate is a necessity.
Have theologians reached out to you at all?
I don't want to go that way. It's yeah.
Can simulation theory align with the Big Bang and our current understanding of the birth of the universe, if you like? Can you?
I get the question. Okay, we have a very deep understanding up to a point. Okay, and then everything breaks down at the singularity of the Big Bang, the wall, and we can't pass beyond that. Okay. So where the simulation comes here, it gives you the easy way out of this, and says simply that what was the Big Bang? It was the moment somebody turned the simulation on, and the rendering of the universe began from there using the laws of the code. So don't get me wrong, I'm not intelligent design and creationist or whatever it is. I think, yes, there is a creation process, but the code and the creation process allowed for an evolution to follow after the initial rules have been given
dispersed.
and dispersed. Then the evolution followed. Okay, so they are both true, you see. That's how I see it. Yeah, but we enter the realm of speculations now. Is not yeah.
So what I want to try and understand is, what are the ramifications, before we finish up, the ramifications for society, for community, for everyone, if we are living in a simulated universe, or is it something that really is irrelevant in people's daily lives, for example?
So this is a question I get very frequently, and almost all the time, actually, because this is what people care about. And it's exactly what you said. It's totally irrelevant to our daily life. It makes no difference to you and me whether we are not or we are in a simulated reality. And the reason is we can't distinguish between what is real and what is not real. We can't tell whether this is the real thing or the simulated thing. There is no way of distinguishing. In fact, it's so complex that we struggle through scientific means to prove this. This is the big struggle in science, to actually find the signatures of these. The only difference you will make is in deep scientific research, trying to understand what we call the laws of physics. We can call them the laws of the code, or the laws of the simulation, if you want. And it opens up a range of possibilities in terms of science and development, because if we actually achieve a deep level of scientific understanding, and maybe we find a way of actually not breaking out of the matrix, but maybe hacking the matrix. That's the word I've been looking for, hacking the matrix a little bit. Maybe we can start making our lives a bit better. Maybe we can start improving the world from within by changing the rules of the matrix without destroying the world. Okay, so bending some of the rules of physics, or maybe if this is how I see it, as a positive thing.
You see it as a useful tool, as
useful
in
tool,
the right hands.
In the right hands, and it can be weaponized. If somebody, I mean, it will be in a fraction of a second. The defense industry will uptake this in a fraction of a second and try to weaponize it. Just think about this. If take our planet and whatever we are here, reality or simulated, okay, the countries that control the most powerful weapons systems on the planet, they kind of is the golden rule. Who's got the gold makes the rules. Okay, so they kind of make the rules, and they're the Security Council permanent members, and the nuclear powers and this kind of stuff. But the country or the the company or the defense industry that controls the code or the simulation or the matrix or hacks that controls not the planet, controls the universe. Yeah. So you will be in a fraction of a second that this will get weaponized before you know it. Yes, I agree with that. So like with everything else, like AI, like atomic weapons, like and atomic energy, like everything else, this could also be, probably used for good things, but
with that harbinger of doom. Melvin, what does the future hold for your work? Where are you going next after Reality Reloaded? What's the future for Melvin Vopson?
In 2022, I proposed some kind of experimental protocol to test some of my ideas, and this is not done yet. So one avenue is I need to secure the funding for this. I even crowdfunded for this experiment. I managed to get 5% of the budget crowdfunded, but it's not. These are not cheap workbench experiments. It takes money. Yeah. So seeking the funding maybe to attempt that experiment, or maybe collaborative groups somewhere else to minimize the cash requirements to build the instrument. So that's one option. So I would like to maybe attempt that thing. And that links up with the mass energy information equivalence principle, showing that information has mass, and the matter has a DNA, informational DNA stamped in every elementary particle and everything. So very, very wacky, very fundamental ideas, but the implications ramifications are huge if these are proven correct. So I would like to try that. The second law of information dynamics, it doesn't need any proof. It's based on empirical evidence and facts that are testable and out there. So it's kind of what it does need, and this is what I would like to work on a little bit more, expansion into as many systems and as many processes as possible to see where it can help by bringing additional tools to physics and to our understanding. And I'm working on something as we speak now on that aspect. On the genetic side, the law has been tested on SARS-CoV-2, which is the COVID-19 virus. Yeah, it hasn't been tested on other genetic systems. It will be nice to expand the validity of these to other bacteria, viruses. It can be applied to cancer research, to all sorts of things. So there is a lot of room for expansion in that area. So I mean, this is a rich, very productive scientific field, because it branches out into so many things: pure mathematics, computational information theory, physics, fundamental physics, cosmology, genetics, and evolution. I mean, it's insane. So I'm not actually running out of ideas what to do or panicking about the future, because I'm quite positive I'll be busy until retirement with this work, and probably never finish everything I want to do. So,
well, I mean, you couldn't possibly finish. I mean, there's no end. It's endless.
Exactly, it's endless. And everybody died unhappy. Actually, the great scientists and physicists, they always felt unaccomplished. They felt like they didn't finish. So yeah, you need a bit of a Buddhistic approach here, sort of like so like just you go in a vicious circle and you never feel, but yeah,
there's always another question. There's always another problem.
And yes, so you need to draw a line at some point. I'm just keeping myself busy with this stuff. Yeah, information physics.
Melvin, we'll put a link to Reality Reloaded in the description box. Thank you so much. This has been absolutely fascinating, and keep doing
Appreciate
what you do.
It. Thank you, sir. Thank you for having me.
My pleasure. Delighted to talk to you.